Hello, everybody. I am here to teach you about water and the fitness of the environment, really just water. Textbooks got more clever of how they name this chapter. Some call it just water, 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 and some call it other random things. But the old title used to be Water and the Fitness of the Environment. And so what we're going to learn today is why water is so important. And water is important not just for one reason, but it's important for 50,000 different reasons. But we're going to learn a few. So water is usually for almost all living things, the biological medium that most biological reactions happen in. Most of your reactions in your body is surrounded by water or has water part of it. Most cells are going to be about between 70 and 95% water, depending on what living thing it is and where it's at. So obviously water is important. Get that across. The most important aspect of water is a very unique molecule. I cannot express that enough. It does things that most liquids don't do. And that uniqueness makes it invaluable to biological living things. One of the most important one is the polarity of water. And when I say polarity of water, what I mean is that water has polar ends. Almost think of like the North Pole and the South Pole of the Earth. And so the North Pole is on one end of the Earth, the South Pole on the other end. They have different charges. It creates a magnetic field. Oxygen has a very similar thing. It has one side of the water is positive and one side of the water is negative. And because of this, because of these attractions, because of these things, water will like to connect to different things based on charges. So this hydrogen here being positive is attracted to this oxygen up here being negative. This is called a hydrogen bond. Now, these are not actual bonds. They're not actually connected. It's more of an attraction. It's more or less, they're just kind of like when you hold two magnets apart from each other and you can feel that pull that want to be next to each other. That's what's happening here, okay? Now, it takes energy to break these, but it's not as much energy as it is to break this HOH here, this water. But this is important. So oxygen is negative, hydrogen is positive. Why that is we're going to learn about covalent bonds, or we did learn about covalent bonds. These guys, oxygen and hydrogen, share electrons with each other. But oxygen is a bully and holds on to the electrons a lot more than it gives it to that H. And so oxygen has extra electrons than normal, making it negative because electrons are negative. Because the hydrogen doesn't have any electrons that it's supposed to be having, it only has that one proton, which makes it positive. So this oxygen being negative attracts other positive hydrogens. This hydrogen being positive attracts other negative oxygens of other waters. So water really reacts in predictable ways with most things. We kind of know how water is going to basically attach or be attracted to things based on its chemical properties. So we use polarity, this idea of polarity, for four major biological principles. There's the cohesive behavior, and we're going to learn that there's also adhesive behavior. The ability to moderate temperature, the expansion upon freezing, and the versatility as a solvent. We'll go through each one of these individually. Cohesion is the act of water actually being attracted to itself, being attracted to other water molecules. And so cohesion, water is connecting to other waters and trying to stay there. One of the more famous ones, if I go forward real quick, is a water strider. So the water is attracted to each other, and the water strider is light enough and spreading out its weight enough where it can't actually break through the attraction between the waters, so they have the ability to walk on water. Now, the other one is adhesion. Adhesion is the attraction of water to other molecules. So the way I remember this is cohesion. It's co, like they're connecting to themselves. Adhesion is like glue. You connect two separate things to themselves. Like I connect like a piece of paper to a desk. I glue it with adhesion. So that's how I remember. So cohesion, adhesion. Adhesion is the attraction between different substances, for example, water and plant cell walls. So if you look at a plant, plants have to get water all the way from the roots to the top. And this is actually a complex process that's really, really important, obviously. because we need plants to do what they're doing. And how they're really doing it is up top here, they're evaporating off water, which seems silly. You want water to be at the leaves, so why are you letting water go? What it's doing is creating negative pressure, like a vacuum or a straw, and it's helping pull water up. And as water is getting pulled up, it attracts itself to each other, but it also attracts itself to the cell walls of the cells that make up the xylem that it goes up. And so therefore it uses cohesion and adhesion to go from the roots all the way to the top. I already kind of talked about surface tension. That's because of cohesion. Now, you guys, as you know, you probably tried, you can't walk on water. Now, there is a limit. There is an ability for a human being to walk on water, but they have to spread out their weight past what is physically possible. You would have to be like 10, 15 feet wide, rectangle, and you have to thin yourself out. That's impossible, obviously. Moderation of temperature. Water absorbs heat from warmer air and releases stored heat to cooler air. So water is something called a heat sink. So water does a good job of holding on to heat and then releasing it slowly over time. And so why this is a big deal, kind of skipping that one, is this guy right here. It helps modulate temperature not only in ecosystems, but in your body as well. And so we'll start with ecosystems here. And so the Pacific Ocean is cold. And so what it's doing is the Pacific Ocean right now is actually absorbing heat from the air to keep the surrounding areas around the ocean cooler than what the actual temperature should be. And then as you can see, as you get away from this ocean, there's no modulation of temperature. Their temperature is extreme. Now this happens in Lake Michigan too. So the closer you get to Traverse City in the summer, the cooler it is because that lake is absorbing the heat from the air. During the winter, it's reverse. Traverse City is always warmer than Kalkaska. I mean, like 98% of the time, because the lake is really slow to cool down. So it's still warmer than the air in the winter. It releases the heat into the Traverse City area, and therefore it's warmer than what it is in Kalkaska. And you see this in ecosystems all the time on a very grand scale. Think of like places that they seem to have very similar temperatures throughout the year. Part of that's where your latitude is, but part of that is how close you are to water. For example, somebody like Seattle. Seattle is at a latitude that is kind of similar. Actually, it's further north than we are. But because of their situation next to the Pacific Ocean, Seattle rarely ever gets below freezing. While we do have Lake Michigan next to us, so that helps us. So we modulate temperature so we're not getting too cold. But if you go to the west of us, like North Dakota, where there's no giant lakes, there's no ocean, North Dakota can get down to negative 80 degrees Fahrenheit during the winter. This last year, when we had those cold days, 2 years ago, I should say, they got down almost all the way to negative 90 because they have no water to modulate them. Also during the summer, they can get as hot as like 110, while here we get complaining of like 90 degrees, but that's nowhere close to what they can get to. So the lakes help modulate us, the oceans help modulate other areas. If you're far away from water, your temperature is really hard to keep at a normal level. This also idea of using heat or water to modulate is in evaporative cooling. So when you sweat, you put water on your skin. That water then absorbs the heat from your skin and then evaporates off and takes the heat with it. That's the idea behind the sweating. And so this evaporative cooling is a useful thing that we can use in our bodies, but almost all animals use. So for example, like dogs, you guys know that dogs pant. And so they're putting the spit on their tongue. They're running about every about 4 or 5 minutes, they're running 99% of their blood through their tongue. That warm blood goes up against the surface. It heats up the water. The water of the spit takes away the heat, and they cool down. So this is something that almost all animals use in some way or some form, is evaporative cooling. It's an easy way to cool down your homeostasis. So water, obviously water helps also modulate our temperature just in general. It's harder for our temperature to go up and down like crazy. I mean, even think about if you have a fever, your fever is within 5 or 6 degrees of what you normally are. That's not a big change. But here, our ecosystem has more of a big change in what the temperature is. And one of the interesting things is how ice plays a role in that too. So ice is unique in its sense that water is one of the only things on Earth that its solid is more or less dense. Sorry, that solid is less dense than its liquid water. Most things, when it becomes a solid from liquid, become more dense and they sink in its own liquid. Water doesn't do that. Water floats. And if you think about that, uh, it's kind of really important. So if Lake Michigan, the top of it, started freezing, and if ice sank, everything below it would be crushed by the ice as it was sinking. That would kind of eliminate life, especially in the beginning when we all were in the water at one point. If ice sank on top of us, that would be kind of a bummer. And so this is kind of an important thing. Also, the ice sitting on the surface, water, like I said, it's a heat sink, even as a solid. So it takes a while for ice to melt, or ice can absorb a lot of that heat. The water underneath stays relatively warm. So, like in the bottom of Lake Michigan, even though at the top it has ice, it's covered in ice, the bottom of Lake Michigan is still about 50 degrees, which is quite, I mean, impressive. Like the top is 32 or even colder. Be 50 degrees down below allows fish to go down there and survive the winter. So they don't die, they don't freeze to death. So this is an example of what it looks like. So when water is turning into ice, they actually set up into this lattice formation and they actually spread out. They become less dense. While liquid water, they're doing hydrogen bonds kind of the same way, but they're bumping into each other more. They're more dense. So that's why ice floats. In chemistry, you guys learn about solution, solute, and solvent. And I just want to put these words up if you want to pause and write them down. These are important words to know. So why they're important is if I look here, water has the ability to dissolve ionic bonds. It has the ability to take in solute, and it's what we call as universal solvent is what water is. But its ability to take in things and dissolve things into the solution. So here is some salt. You'd see this is what salt normally looks like. NaCl, and NaCl disassociates in water, so they break apart. Na comes here. Na is positive, so you know the negative oxygens are going to be all over that. And then the Cl negative, it's negative, the positive hydrogens are going to be all over that. So you even know what the waters are going to do around it. They surround it and it becomes part of the water, and that's why it goes invisible. Water can also work on larger molecules. Now, I talked about polarity earlier. So things can either have a charge and be polar, or things can be without a charge and be nonpolar. Things that are polar, water loves. And so it actually interacts with those things. This is a polar protein here, a polar enzyme, and you can see water interacts with it. So this enzyme definitely interacts with water. It needs to probably work in water. There's a reason why it does that. Now, there's also nonpolar things, let me get through those, that water just doesn't like. And when we say hydrophilic, what we're saying is that's something that likes water. Hydrophobic is something that does not. And we've learned about hydrophilic and hydrophobic before. Hydrophobic are things like lipids, oils, stuff like that. Hydrophilic are things that like water, so like salt, sugar, and whatnot, carbohydrates. Now, what's interesting about hydrophobic, hydro meaning water, phobic meaning scared, you would think that the lipid is actually scared of water or doesn't want to interact, but it's actually vice versa. Water does not want anything to do with it. So it's water that's choosing, if you want to give it like a human quality, not to interact with oils or lipids. Water also has a unique ability itself to disassociate, and this is why it's so important in acid and bases. And so two waters can break apart when they're attraction and become H3O, or sometimes in chemistry we write this as H plus and OH. H plus or H3O is acidic, OH is basic. So these things, this helps buffer, if you remember that term in chemistry, helps buffer acids and bases. And acidic solutions, basic solutions are important in living things because we need to stay in a value set. Most biological things are anywhere really between 6.4 and about 7.6. It can go a little bit lower and higher, but that's usually where it's at. And so water helps keep us in that range. And so when water interacts with, say, a base, it interacts with that base and turns it from, say, like pH of 12 down to a pH of 7 or 8. And so water does a good job of buffering, is what it's called. So you kind of see the scale of pH here. So buffers are substances that minimize changes in concentrations of H plus and OH in a solution. So realistically, water does a great job in your body because you are constantly taking in things that are acidic and basic. And it's making sure that your body doesn't become too acidic or basic. Think about what you might have had this morning, like you had coffee or pop or something like that. That's a pH of about 2 or 3. It's very acidic. Or you might have had you're breathing in and out CO2 and oxygen. Those are also acidic and basic. Those have properties that can affect your acidic level or your pH level. And so water has to balance that out in living things. And that does a good job of doing that. So realistically, water is super important. And so I can't get that across enough. This is just one video. This is my video. I'm also going to post another video I would like you guys to watch. But it really, at the end of the day, comes down to this idea of hydrogen bonds. Water is polar. It has a positive side and negative side. The negative side is going to interact with positive things. The positive side is going to interact with negative things. And this kind of dictates how water treats different things. If these two things, this positive, negative thing, comes across something without a charge, it just passes it by. And so all these things that we just talked about, all these different random things that water does, it all comes back to this picture. So I hope this helped a little bit. I hope you took some notes. Like I said, I'll put a little video up as well to kind of help you guys. And the reading hopefully will help to get this across. All right, guys. I hope you guys have a wonderful day. Hope you guys are doing great in class. Thanks.